Hello everyone, I am Saket Kumar Singh. I am working as an assistant professor in Department of CSE Ajay Kumar Garg Engineering College Ghaziabad. Okay, so in this lecture I am going to discuss about cache memory management, and where do this cache memory lies inside the memory hierarchy, how it is useful, and what is the main important thing that we use cache memory, what will happen if we will not use cache memory. So we will discuss all the things, all the related things about cache memory in this lecture. So let us see the outline for this lecture. So we will first discuss what is cache memory, and then we will try to discuss where as we have already seen this when we have seen this in unit 1 chapter 1, that is your introduction to operating system. In lecture number 3 we have seen the memory hierarchy, but we will again briefly see that where it resides inside the memory hierarchy. Okay, what are those caching operations? What are the caching operations that computer performs, and where are the scenarios where these caching operations are performed? Various levels of caches like L1 caches, L2 caches. In lecture 3 I told you that I will go in details in later on when we will talk about this cache memory management. Okay, so we will see various levels of caches, and then we will see different cache mapping technique. Okay, so first is your direct mapping, second is your associative mapping, third is your set associative mapping, and last we will see locality of reference, what is called as locality of reference. Okay, so now let's start with this cache memory. What is a cache memory? Okay, so it is a high speed memory designed to match the speed of the CPU, because we all know that CPU is very fast, and main memory is connected to the CPU with the help of a system bus. So for a transfer rate of a system bus is very low, it is considered to be an overhead. If you want, if CPU has made some request for some data bunch or something, then if that data is available at the main memory, so that can be communicated through the CPU with the help of the system bus, and that will take a lot of time. So the idea is to just keep a fast memory nearer to the CPU, so that it contain the frequently needed data, so to avoid the repeated lookups inside the main memory. Okay, so you can see it is a high speed memory designed to match the speed of the CPU. Okay, it reduces the system bus overhead, that I already told you. Like suppose in a program there are again and again some line of instructions are called. So why to go again and again using this system bus? Why to go inside the system bus again and again and to look that particular data or instruction in the main memory? Why cannot we keep that data or instruction nearer to the CPU to avoid this system bus overhead? Okay, it is expensive than main memory and cheaper than CPU register. So that I will show you when I will discuss the memory hierarchy after this slide. Okay, but for now you just remember that cache memory is expensive than main memory. Main memory refers to as RAM, and cheaper than CPU registers. It is mostly managed by hardwares. A little bit of operating system intervention is there, but mostly a cache memory is managed by hardwares. Okay, it reduces average access time. Suppose a CPU wants to access 16 KB, then what the average access time to access that 16 KB will be reduced if we are using this cache memory. Okay, so it acts as a buffer between main memory and CPU. It contains frequently needed data and instruction. We will see the example after this slide. Now first see where does it resides in the main memory hierarchy. So you have seen this memory hierarchy. This image has been taken from the Tenenbaum book. So you can see this is your registers which are considered to be very fast, which are inbuilt on the processor chips as well. After that, the second hierarchy is your cache, then your main memory, then magnetic disk. So what is the access time of a register? It is 1 nanosecond, then a cache is 2 nanosecond. You can see it is the access time for main memory is 5 times more than the cache. Okay, and this is 10 you can see this is 10 microsecond. Now capacity, you can see how the capacity is varying. Registers are less than 1 KB, cache can be 4 MB to 16 MB, main memory can be 1 to 8 GB, and hard disk can be 1 to 4 TB. Apart from this, you can also relate how costly and memory is. Register is considered to be very costly, then cache memory, then main memory, and then magnetic disk. Okay, so you can see figure 1 memory hierarchy. Now I have also drawn you can see this CPU is connected through the main memory using system bus. Okay, and it is main memory is connected to the secondary memory. Okay, so this is the hierarchy. Now where does cache reside? Cache reside in between the CPU and the main memory. Okay, so what are the caching operations? You can see main memory is divided up into cache lines, typically 64 bytes with addresses 0 to 63 in cache line 0, 64 to 127 in cache line 1, and so on. In this way cache line is divided, and most heavily used CPU cache lines are kept in high speed cache close to the CPU. Most heavily used cache line are kept in high speed cache close to the CPU. If a process requests a memory word, the cache hardware checks to see if the line needed is inside the cache or not. Okay, what if it is inside the cache? If it is found, then it is called a cache hit. Okay, then request is satisfied from the cache itself. No need to go and look about the information about the request inside the main memory if it has been satisfied from the cache. Okay, no memory request is sent over the bus to the main memory to look up. Okay, cache hits normally takes about 2 clock cycles, and if cache misses happens, then cache misses have to go to main memory. Like if some request cannot be processed from the cache, then you have to go and find it inside the main memory with a substantial time penalty. Of obviously, if you are going into main memory using a system bus, the time we have already seen in the memory hierarchy how the time is different about cache and main memory access time. So some machines have 2 or even 3 levels of cache, each one slower and bigger than one before it. Okay, so we will see when we will see the levels of cache. You can see caching can be used in other areas also apart from cache lines of RAMs. We will see these areas like whenever a resource can be divided into pieces, some of which are used much more heavily than others. Caching is often used to improve the performance. For example, you can see most operating system keeps pieces of heavily used files in main memory to avoid having to fetch them from the disk repeatedly. Okay, there also you can apply this caching concept. Similarly, the results of converting long path names, like here you can see this is one of the path used in the system, into the disk address where the file is located can be cached to avoid repeated lookups. This is another scenario where you can apply caching. This is and one more scenario, like when the address of the web page, that is your URL, is converted to a network address, that is your IP address, the result can be cached for future use, that we use generally in our daily life when we are accessing some websites on web browser. Okay, so various levels of cache. What are the various levels of cache? We first see what is L1 cache. L1 cache means level 1 cache. these are considered to be very fast. Size are typically 16 KB each. Okay. Access time is similar to process register because these are generally built on the processor chip as well. So, access time is similar, very much similar, not same but similar to the process register. This is built on to the processor chip. L1 caches are built on the processor chip as well. Build using static RAM. Static RAM is used to build a L1 cache. L2 cache. What are L2 cache? Holds up to several megabytes of frequently needed memory words. Okay, and housed on processor chip as well. L2 cache are also reside on processor chip. Okay. Access time is less, around 2 clock cycles as compared to L1 cache. Suppose if CPU has made some request, if it was found in L1 cache, no need to go and check inside the L2 cache. If it was not found in L1 cache, then the CPU will go and find inside the L2 cache. If it is not found in L2 cache, then it will go in to if L3 cache if L3 cache is there, otherwise it will go to the main memory. Often shared in different multi-core architecture. When we are using multi-core architecture, L2 can be dedicated also or can be shared also among different cores. Okay. Various multi-core architectures also uses shared L3 cache. Suppose if there is a multi-core architecture which are using L1 and L2 dedicated cache, dedicated means like quad core is there, like 4 cores are there, all the 4 cores are having their separate L1 and L2 cache and a shared L3 cache. Okay, so generally these L2 and L3 caches are shared in multi-core architecture. Not sure about L2, but L3 is definitely shared in multi-core architecture. Okay, different cache mapping techniques are, first is your direct mapping. So, what is this mapping? I hope you all have studied about paging concept in your memory management. So, at that paging we logically divide the process into n number of pages, and we have to bring that pages into the main memory for faster access of those pages. If CPU has made some request, those pages should be accessed fast. So, how to keep all those pages inside the main memory and how CPU will refer to that page, there we have studied some of the basic concepts like what is page number, what is frame number, and what is how many number of bits are required to represent logical address and how many number of bits are required to represent the physical address space. So, similarly here also if you are bringing something inside the cache memory, here also you have to apply some of the mapping technique. So, there the mapping technique was known as paging. Here we directly do the mapping with the help of 3 techniques. One is your direct mapping, second is your associative mapping, or somewhere we can find fully associative also, and then set associative. Okay, or k-way set associated, sometimes it is called as k-way set associative. Okay, so now direct mapping maps each block of main memory into only one cache line. Okay, so how a direct mapping works? It maps each block of main memory into one cache line. Okay, in this mapping, main memory blocks are copied to a fixed block of cache memory. Main memory blocks are copied to a fixed block of cache memory and one at a time. Like if you have divided the main memory into n number of blocks, each block will go on a specific cache line. It will not change every time. It will, like if you have divided the cache into 4 groups, okay, and if the first cache block, you can see you can divided the cache into 4 blocks. Okay, so in the first block, if it is going B1, B2, B3, the blocks that you have logically divided in the main memory, if you will bring that block, that will take the fixed location. It will not behave like B1 will first comes inside block number 1 in cache, and next time it will come inside block number 2. The blocks in the cache are fixed, the cache lines are fixed. Okay, this will be more clear when we will see the diagram. Okay, so how it is decided that the memory block that we are bringing from main memory, we have to keep in which of the block inside the cache, that is decided by using this formula. Okay. So now let's see how it is. CB is the cache memory block number, and to get the cache memory block number or the cache line in where you have to bring that main memory block, that can be calculated with the help of this MB. MB is your main memory block number. Okay, and mod C, where C is the number of cache lines. So now let's see. This is an diagram I have drawn. This is a scenario I have taken. This is a main memory of 128 words, and this memory is word addressable. Word addressable means all the memory, each and every block of memory containing what? These containing 4 words. You can see W0, W1, W2, W3, W4, W5, W6, W7, W8, W9 and so on. This will go. Okay. So the memory is having how much capacity? 128 words. Okay. And 128 words, and each block of the memory that we have divided, so each block will contain 4 words. So how many blocks will be formed? How many blocks will be formed can be calculated by 128 divided by 4, that will be your 32. Okay. So 32, you have divided the memory into 32 blocks, and each block is having 4 words, and total number of word is 128 words. Okay. So now this is your cache lines. So how we can divide the cache if this cache is of 16 words? If the cache capacity is 16 words. Okay. So if this is 16 words, remember the concept of paging, the block size. Okay, at there we use the page size and the frame size is always equal. Similarly here the block size and the cache block size or the cache line size will always be equal. So how many number of blocks we can divide this cache? 16 divided by 4, as each block are containing 4 words. So similarly, if we will bring this block here, this will take the same space here also. Okay. So 16 by 4 will be 4. So we have divided this block into this cache into 4 block, or you can say 4 cache lines are there. Okay. So now we will see that if we want to bring this block 0 into this cache, how we can bring? Using this formula. What is this formula? Like suppose if we want to check for main memory block number. So if we want to check block 0, so block when we'll check about this block 0 mod, what is the number of cache lines? 4. So 0 mod 4 will give us 0. So we will bring that B0. So you can see B0 has been kept on this line number, cache line number 0. Okay. So we have seen this, and another concept is tag. So just remember the concept of paging. The concept of paging was like there was a physical address. That physical address is the number of bits that are required to represent the blocks of the main memory or the pages. Similarly here also there are 128 words. So to represent 128 words, how many bits are required? 7 bits. Okay, 7 bits are required to represent 128 words. Okay. So we have to divide it into page offset and frame number. Okay. So page offset, what is page offset? Here it is block offset or size of the block. So how many blocks are there? Means how many the block size is what? Block size is 4 words. Okay. W0, W1, W2, W3, 4 words. Okay. So what is the block size of the block? 4 words. So 4 words, to represent 4 words, how many bits is required? 2 bits. 2 bits like 0 0 0 0 1 1 0 1 1. So 2 bits are required to represent the block size. Okay. And the remaining you will keep here. So similarly in this direct mapping, this paging concept, you can relate it to paging concept. Here you have included this tag. What is this tag? So we have kept the 2 as it is. 2 will represent the number of bits required to represent the block size, and this 2, this 2 is representing the line number. Line number means which at which cache line location the block is residing. Okay. So, if how many cache lines are there? How many cache lines are there? 4. So, to represent this 4, how many bits will be required? 2. So, total number of bits when we talk about this paging concept, when we talk about this paging concept, okay, when we talk about this paging concept, the frame size and the frame of page size and the page offset, you keep it as physical address, like page offset is here and page size is here. Okay, sorry, page offset is here and page number is here. Okay. Similarly, here also if it is 32 blocks, okay, and each block is having 128 words. So, 128 words. So, to represent the 128, how many number of bits will be required? How many number of bits will be required? 7. To how to divide this? We have to divide this. This will contain the block offset. Block offset means the size of the block. Size of the block is 4. So, to represent 4, how many number of bits are required? 2. So, what are the remaining bits? It is 5. So, this is according to the paging concept, but we are not using the paging concept here, but it is similar to paging. Okay. So, here in this direct mapping, we just divide this 5 into tag and line number. So, line number, how many cache lines are there? 4. Okay. So, for representing 4, how many number of bits is required? 2. So, you can see I have included this 2 here. Okay. This 2 is fixed because the page size, the block size will always be equal to the cache line size. Okay. And this is your line number. Line number is your representing the number of bits required to represent the line number. And this tag, what does this tag represents? This tag represents, you can see tag bits represent which blocks or the specific word, which block or the specific word can come in a specific cache line. Okay. So, this tag bit, for example, suppose if you want to check this B0, so how the CPU will give the request? 000, okay, 000, and line number is also 0, first line is 00, okay, and B0 means the block size is W0 for representing the W0, 00. Okay. So, this tag will be fixed, this will also be fixed, this will give you the variation of 01, 10, 11. Okay. So, now let us check, all the things are 0, that means this is your block 0. So, block 0 is situated at line number 1. Okay. Now, what is this represent? 0 0 0 0 0 0 0 1. So, this is representing your block number 1. So, where the block number 1 will go? Block number 1 can go where? Okay. Now, let us take the case of this B4. So, when you take the case of B4 is situated at line number 0. So, the line number will be 00. Okay. What is this tag? What does this tag bit will represent? 0 0 1 0 1. So, this will give you 20. Okay. So, we have to keep this 0, we have to keep this 1 and then 00. So, in this way a CPU will generate the request. In this way the CPU will generate the request. This 00 is the tag bit, this is the line, this will represent the line number in which line number the item is present, and this will vary according to the number of words, like 00, 01 will represent the W1, okay, 10 will represent W2 and 11 will represent the W3. Okay. So, when you will convert all these into decimal, you will get the specific word, and that specific word belongs to some block. So, which block which block is residing at which cache block can be get through this reference. So, in this way the pages are referenced by the CPU in direct mapping technique. It is very similar to paging in memory management, but we divide block number into tag and block bits. Okay, what are the advantages? Advantages are searching is fast due to tags, because whenever you go and check the tag, if the tag is matching, then you are having a cache hit. If the tag is not matching, no need to go and look for the word inside the whole cache line. Because and the disadvantage is conflict miss, as the lines or blocks, lines for blocks are fixed. Like suppose in the previous diagram, if B0 is here situated here, B0 is sitting at this position and B4 comes, okay, suppose all the cache lines are empty, but if B0 is located at this line number 0 and B4 comes, you cannot put this B4 on other lines, you have to put this B4 in this line always. Okay. So, this is conflict miss, you cannot put the B4 when B0 is already sitting, you have to pull out the B0 and then you can give that cache to B4. Okay. So, you can see if a block maps to position in cache where a block is available already, this block will not be added in cache even if whole cache is empty. This is the biggest disadvantage. So, now the next technique is associative mapping. In associative mapping, main memory can be copied into any block of cache memory. There is no any formula, as you can see B0 can be copied to cache line 0, 1, 2, 3, any places. Replacement algorithms can be used to replace an existing block in the cache when the cache is full. Okay. Those generally LRU are used in cache mapping techniques. Cache hit increased. Why? Because the conflict, the previous disadvantage has been removed from here. What was the disadvantage? Conflict miss. Okay. So, in associative mapping, cache hit is increased. Tag bit length is now increased, because here you can see what is the difference between direct mapping and associative mapping. You can see tag bit is now 5, you can see this is 5 now, means you have added the tag number and the block number, line number. Okay. Because as it go in any location, so no need to check for different line numbers, so the tag size has now been increased. Okay. So, what is different between direct mapping and associative mapping is this cache line. Okay. Now, the last topic is your k-way set associative mapping. In k-way set associative mapping, it is the combination of both direct mapping and associative mapping. Here you can see, let me go directly onto the cache is divided into sets. You can see this is your set 1, okay, this is your set 1, this is your set 2, and after dividing the cache into sets, then we will apply the associative concept. Like when you have divided the cache line, then you can put B0 anywhere, B1 anywhere. Okay. When you have divided the cache line into sets, so when this k-way set means how many times you are dividing the cache. Here I have divided the cache into 2 sets, so this is 2-way set associative mapping. Okay. So, mapping function allows a block of the main memory to reside in any block of a specific set. So, this B0 can reside in any block, but not in set 2, only in set 1. Okay. If set size is 2, it is known as 2 set associative, and if its set size is 4, it is known as 4-way set associative. Cache memory set number you can get the set number by main memory block number mod cache memory. So, you can see how the reference is different from the previous 2 mapping techniques. Here 1 bit is required for your set number, block size will be, block offset will always be same as 2 bits, because each block is having 4 words and the tag is 4 bits. So, now this is locality of reference. Generally it is of 2 types. Let me go directly on to that. First is your temporal locality of reference, and second is your spatial locality of reference. So, temporal locality of reference, generally LRU is used. It just suggests that if an item is referenced, it will tend to be referenced again soon. Okay. But in spatial locality of reference, if an item is referenced, items whose addresses are nearby will be tend to reference soon. So, like if you have written some program and this line is being executed, then referencing of this or this line will be more probability will be more in when you talk about this spatial, and when you talk about temporal, it depends on the item which is referenced, it will tend to be referenced again soon. So, generally LRU is used when you talk about temporal locality of reference. Okay. In spatial, words in close proximity adjacent will be accessed next. Keeping more words in blocks affects the spatial locality. Okay. Examples are arrays and programs, while temporal examples are loops which are repeatedly called, subroutines, etc. Thank you for this lecture.